All right, so here is a new day, new problem for us to work on. So we currently have a tank that has three different flow rates coming in, one, two, three. And so that means technically different temperatures, different concentrations, all that jazz. And we are assuming it's continuously mixed, which means that it is all one concentration coming out, and the height is changing, but our cross-sectional area stays the same because the tank is staying the same. So we are going to look for our change of height. We're going to use that in our change of concentration and our change of temperature. And so with all of this, we're assuming that with these three flow rates that the densities are the same. So we're not going to move around with density. So to start, we're going to have to look at our change of volume over time. So first things first, let's go dV over dt. And so this would technically be where we put our flow rate in and our flow rate out. Well, a flow rate in is three different flow rates, which would basically look like Q1 plus Q2 plus Q3 all minus Q out. Now, when you look at this, there's an easier way to say this, and it's also going to make life a lot easier when we code because we can change the number of iterations if we do it as a summation. So we're going to say that that is equal to the summation from I equals 1 to 3 of Qi and then minus Q out. That's just going to make our life easier in the long run. And so from this, we can get our change of height over time like we did in the previous problem that I have posted. You pull out your cross-sectional area because your cross-sectional area isn't changing. It's just the height that's changing. And so when you pull that out and then divide it onto the other side, you have dH over dt is equal to our summation. That was a bad summation, but it's fine. Minus Q out all over AC. And so we're going to use that in all of these two. And I say all of them, but there's only two. So we're going to use this to help us with that. So the next thing to consider is our volume times our concentration. So everything is kind of correlated with volume, which is why our height's going to have a play in it. So our next thing we're going to look at is dVCA over dt. So the change of volume times the concentration over time. And so we're going to take all of this, and it's basically just multiplying it by concentration. And so all we have to do for that is we do our summation. Now see, that was a good summation of Qi times CAI, and then minus our Q out CA, or C out, whichever way you want to say it. I'm going to do CA out so I don't confuse myself. All right, and then all we have to do is do the same thing we did up here, which is pull out the AC, the cross-sectional area, and then divide. So it ends up being DH, and then all of this over our cross-sectional area. Now, we're going to apply the product rule to separate this out. And so that would be CA DH over DT plus, I believe it is H dCA over dt. And so with that, we have separated this out, and so we can use that from what we calculated. Where did I put it? Right here. All right, and so when we do this and move everything over and then divide by the cross-sectional area, we get, well, let me just put quotes right here just to make life easier. I'm not going to rewrite that. So what we're going to do is we're going to subtract this over here and then divide everything by H. And so what we end up getting is dCA over dt. That is equal to 1 over H multiplied by okay. Sorry, I was just double checking what I was doing because I was second guessing everything. All right, summation. QI, CAI minus Q out, CA out, all over AC, and then we have our minus CA DH over DT in parentheses. Can you see that? Yes, you can. Okay, so that is for our concentration. And so really quick, what I'm going to do is I'm just going to erase what I have, leave this guy and this guy, arrows, Andrea, and then we're going to derive our temperature. All right, so I've just moved everything up so we have space to do our dt over change of time. So change of temperature over change in time. So what we're going to start with this time is we are going to do our dV like we did before, but we're going to put in our density, specific heat, and temperature all over change of time. And so we do the exact same thing as we did before as plugging all that in and adding it to basically our QI and Q out. So we have our summation. Whoops, sorry. That was kind of messy. We have our summation, I equal to 1 to 3, QI, density of I, specific heat of I, T of I, minus everything else, but I'm going to give you, you're going to struggle to see everything, but basically it'll be that minus the same thing, but for just Q out, so out, density, CPT. And so I know that's messy, but our specific heat and our density, we're assuming, are the same for all flows. And so with that, all we do is we're going to cancel this and this. Oh, not the T. Sorry. Whoops. Not our temperature, because that is what we're looking for. And that. And so I'm just going to erase this and rewrite it to make my life easier and make sure we have enough space over dt is equal to summation I 1 to 3 QI temperature of I and then minus Q out T. And so same thing as before, same pattern, product rule to separate this out, which is where, wait, did I? Yeah, wait. No, correction, not product rule yet. We have to take out our cross-sectional area, so it's a change of height. I was wondering why. I was like, wait, the V's can't cancel. And okay, so we're going to pull it out and then divide. So all of this 1 over AC, change that V to an H. And then now, sorry, my headphones are falling out. And that's where my mic is. And so now we do the same thing as before, where you do our product rule. So we have T dH over dt plus H dt over d time is equal to that. So is equal to that. And then do the same thing as before. It's a pattern. So where you subtract this over to here, and then you divide everything by the height. And so that's going to give you our change of temperature over change of time. That is going to be equal to, I'm going to write it this way for consistency purposes. 1 over H, parentheses, 1 over AC, another parentheses, summation I from 1 to 3 of QI, TI minus Q out, T, and that subtracted by our T, DH over DT. and close parentheses. So we have this guy, which correlates to this, and then we also have this, which will put that in as well. And so this is all we need for our code in Python. And as I did with the last video, I'm just going to write 1, 2, 3, those 3 equations on my board, so that when I'm looking over there, you know that that's what it is, just because I don't want to mess up any of the multiplications, or just, and I don't want to mess it up because I already struggle enough with coding in general. So let's go and code it. Alright, so now we are going to code this in Google Collaboratory. So I've already imported all of my general coding stuff, so NumPy, subplots, IVP, root, all that jazz, and then we have all of our initials and constants. So we have gas constant, all of the initial values for each flow in the form of an array. So this is the first flow, this is the second flow, this is the third flow, and then these are when our flow of the second one changes, but everything else stays the same. So we're going to put in all of our equations we just derived, and so we have defining, we're going to call it change, and then the variables to input should be time, because everything's reliant on time. We have a vector. We're going to have Qn naught. We have CA in naught. And we have T in naught. And that should be everything. All right. Oh, I put Chung. I need change. All right. Cool. Let's do what our vector is. So our vector is going to be our height, our concentration, and our temperature is equal to V. All right, next is putting in our D8, nope, our Q out. And that is the area of our hole times 2 times G times H to the power of 0.5, because it's under a radical. Now we put DH. So DH is our NP.sum of our Q in naught values, and it is that minus Q out, and all of that is divided by our, cross-sectional area. Cool. All right, next, DCA. That is, I'm going to do it this way. I'm going to be 1 over H, so times and we're going to do NP.sum of our Q in naught times CA naught, and that parentheses minus Q out times CA, that, and then divide that by cross-sectional area. And then within this, we also subtract our CA times DH. All right. Oh, sorry, CA in naught. And then we also have our change of temperature, which I'm going to copy and paste this and just adjust accordingly because it makes my life easier. So instead of CA in, it is, oh, I didn't want that. Temperature, no, not RT. And then this is also T. And this is also T. And then we are going to return an array of our DH, our DCA, and our DT. Shift Enter. Cool. All right. Sorry, I can't sit like a normal human. I have to sit weirdly. All right. Let's do, sorry, I have a bug bite on my arm, and that's what I was looking at. All right, now what we are going to do is we have to do our root stuff. And so what, I'm going to say sol is equal to NP dot. Oh, I don't need NP, I just need root. Yeah, because we did that. All right, and then we have lambda of V, and we do change of 0, B, Q in naught, CA in naught, T in naught, and then boom, we have to do NP dot array. Okay, not array. Whoops, wait, yes array? No array. Yes array. Sorry. It should be parentheses, bracket, and then be this because it'll be np dot sum of our q in naught, close that parentheses, you divide it by our area of the whole. Alright, and so there's that. You do the exponent of 2, there's that, divide it by 2ng. Alright, and then we have some initial states, so 0.5 and 70. Shift enter. Alright, then we have our result, and that is going to be our solve IVP. And that is going to be, we're going to do our lambda, and this is going to be t comma v. And we do change, and then it's just our units. All right. We have that. We have our t-span, which is 0 to, I don't know if I actually need to put those in. It might just be change. If it yells at me, I'll try that. T-end, and then we have our y initial, which I believe is our solve x. Oh, sorry, my phone vibrated. And then method is Radow, and then dense underscore output is equal to true. Shift enter. Oh, it's not mad about it. Maybe that worked. I don't know. All right, let's now graph it. So we have fig is make underscore subplots, and since we're doing 3 of them, we have to do our rows equal to 1, our columns is equal to 3. All right, and then we have fig dot add scatter, and we have to put in our x value. Beep beep whoop, Andrea, you forgot t-plot. I have to define our plot. So linspace is 0 to tn, and let's do about like 1,000. All right, and then we have to put in our other values, which is going to be our h plot, our ca plot, and our t plot, temperature plot. And that is going to be equal to res dot sol of t plot. Shift enter. Are you gonna yell? No? Okay. Doing okay so far. Alright, now we can do our x is equal to t plot, and then we do our y is equal to h plot, because this is the first plot. And then we define it a row and column, so row is equal to 1, column is equal to 1, and that should be good. Alright, and then to make my life easier, we're going to copy and paste it, and I'm going to just change the variables. So this needs to be CA plot, and our column needs to be number 2. This is our temperature plot, and our column needs to be 3. Shift enter. Ooh, nope. All right, let's see. Where did I go wrong? Oh, 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 2. There we go. Okay, I was about to say some weird stuff happened there. All right, so here is our height. This one is our concentration, and this one is our temperature. And so if you look at these with our initial values, so our initial values and then it changes our, we change our flow rate. So if you look at it, our temperature, the average of the 3 is right around here, and because when you do the average and then you change the flow rates and you basically decrease the amount of the lower temperature and then increase the amount of the 80, it's going to be a little higher up here. And then as far as concentration goes, its concentration stays the same, but the flow rate changes. And so when you change the flow rate and you increase the amount of 0, so yeah, so you're increasing the amount of concentration of 0, so it's basically like we're adding just straight water, say something like that. And then you have a full one, you're decreasing the amount of full and keeping that the same, so pretty much it should be lowering from what it's initially at, which is doing. And if you look at these, it's a pretty small amount. It just looks big based off the scaling. And then lastly, as far as our height goes, so it's flow pretty much, and it's volume. And then if the flow, this is going to happen pretty much regardless, it'll even out. All of these will reach equilibrium or close enough to it. So that is how we graph this problem, and then we will look back at the whiteboard and look at our other problem. All right, so part C of this problem, we are looking at a similar situation, except that we have one flow rate in. We have an overflow system in place, which means that the volume is constant. And so I'm going to put right here, CA out is equal to CA in, and that V is constant. Okay, that's why the valve's up there. And then continuously mixed, so the concentration is consistent throughout. And then we also have a cooling jacket on this tank. And so we also have to take that into consideration, and that this reaction is exothermic from A to B. And so what we're going to do is we're going to basically derive the time-dependent concentration as well as look at some energy balances. So we're going to end up looking at our change in concentration and our change in temperature. And so first things first, we're going to put in our Arrhenius equation. So just to write it down, I'm just going to abbreviate it because honestly, I don't trust myself to spell it right. So we have our K is equal to K naught the e to the power of, and I believe it's negative. All right, so we have that in play. And then we also have to look at our overall mass transfer coefficient. And so we're going to look at our flow is equal to U, which is our overall mass transfer coefficient, A. And then within that, we have our temperature in the moment as well as our temperature from the reaction. And so that's, we're going to say that's T minus TE. All right. And so let's look at our change in concentration. So our dCA over dt. And so to start with, because our volume is constant, we don't have to put it behind the differential like we did for the previous problem. We'll write through, and so we just put the volume dCA over dt. All right, because that means we don't have to mess with our changing of height because we have that overflow system in place. And so what we're going to do is we have our flow rate multiplied by our concentration of A minus our concentration of A. I'm going to call it CAN. Yeah, let's call it that. And wait, whoops, reverse it. Beep, beep, reverse. All right, it is CAN because we're, if I'm calling it CAN, yeah, Andrea made a mistake, whoa. And then we have our volume, K, C, A. All right, so from here, we just take this V, take it to the other side, and so we have our change of concentration over change of time is Q over V, CAN minus CA, and then minus, the V cancels, KCA. All right, and so what we're doing, I never said, why do we have to incorporate the volume even though the volume is constant? So yeah, it doesn't have to be under the differential, but we still need to take volume into consideration because of the size of the reactor. So that's still going to change things. Because if you think about it, when you have a coolant and you have it at a certain temperature, the volume still has a play in how quickly the reaction is going to cool down, right? So that's why we still have to take it into consideration. Okay, so next part is same thing, but with temperature. And so the temperature one is a little trickier. So what I'm going to do is I'm going to move this up here because I feel like I'm going to need all the space I can get. So see you in a moment. All right, so I just moved this up there. I kept our mass transfer coefficient in there so that I don't forget it because I can almost guarantee you I will. And so what we're going to do now is we're going to look at our change of temperature. So similar to what we did in part A/B is we're going to add in our density, specific heat, temperature with the volume. And so as before, since there's only one flow in, we can say that the density is constant, that the specific heat is constant, and obviously volume is constant. So we pull it all out, and the only thing that is within the derivative is the temperature. And so we have our density, specific heat, and volume with our change of temperature over time. And so what we're going to do is we have to add in basically this, that similar situation, and this. So there are three different parts, okay? So we have our density, specific heat, we have our T in minus T, and then we subtract it by something similar to this, but it's going to be our delta H and R. Well, that's, we add that, sorry. Rewind. Subtract that. So minus UA, T minus TE. All right, and then we add in HR times our K, our VKCA like before. All right, and so constant, these are constant, but now whenever we divide this over, it'll cancel from here. The V will cancel from here. So it'll kind of be a little tricky. So let's take it slow, Andrea, because I will mess up somewhere. I can almost guarantee it. So that cancels and we leave our volume. I forgot my Q. Yeah, whoops. I already forgot something. So that cancels, and so we have our Q over V, same as before, Tn minus T. And then over this, nothing really cancels. So it is everything over that. So minus UA, T minus TE over R It is density, specific heat, and volume. And then with this, our V cancels, but nothing else does. So we add our da 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 da, and then KCA, I'm running out of space. And then so if just the volume cancels, we have density and specific heat. So those are our two equations. We have this friend right here, and then this friend. And those are what we're going to use to code in Google Collaboratory. All right. So now we are going to code part C. And so again, I just put in all of our general coding stuff. And then I also put in our initial conditions. And so we were given this chart, pulled all the information out from this, as well as the stuff from up here. And so we have initial flow rate, initial concentration in, temperature, volume, density, which is rho, specific heat, negative HR, all that jazz. So just copy and paste that in because, again, I'm sparing the time of me looking back and forth. And so, again, I have my lovely whiteboard that just has, if you can even see it, my DCA and my DT, and that's all it has on there. Oh, did I horribly mess up my screen? No, you can still see what I'm doing, so we're good. I think, wait. Yeah, you can still see what I'm doing. All right, so let's start by defining our problem. And again, I don't know, let's just do EQN equation. All right, and we're gonna do our T and V, and that's because we're gonna do another vector. And so we're gonna do, we only have our two variables, which is our concentration and our temperature. And that is vector. Cool. I don't know, why are you capitalizing? There we go. Jeez, I don't know why I was doing a weird capitalizing. All right. Now, actually, I probably should do vector because I do actually have volume and I don't want to accidentally not capitalize something or capitalize something and have it mess everything up. So we have that. All right, and so now with that, we are going to start putting in our problem. Wait, no. We have our K, which is our K naught times NP dot exp, so to the exponent. And that is to our negative ER over T. Yes. Okay. Now that we have that, now we can start doing the other stuff. Again, glancing at my two equations that I have written down. So our change of concentration is our, I'm going to just do it like this, Q over V. Oh, why'd you put enter? Cool. And that is multiplied by CA in minus CA. And that is subtracted by V times K times CA. All right, and now it's time for our change of temperature, which is our Q over V times T in minus T. And then subtract our UA times T minus TC, over, we have our rho times CP times volume. And then we have plus, and this is our negative HR. And it is that times our KCA divided by what was left, which was our rho and our specific heat, because our volume got canceled. Okay, and so we're going to return np.array, and that's going to be dca and dt. Ooh, all right. I'm kind of surprised that that went on the first time. Let's hope that it's fine. All right, result. Solve IVP. All right, so now it's our solve IVP, which is going to be our equation, and then our t-span, which is 0 to t end, and then we have our initial y, which is don't remember yet. We'll take a moment. And then its method is equal to redo. And then we have dense underscore output is equal to true. All right. And then the equation, I believe it should be np.array, parentheses, boom. I believe it would be CA naught, CA naught, and T naught. Nope. Oh, I'm dumb. There we go. There we go. All right. And so now we get to graph. So our t-plot is equal to our np.linspace, and we have from 0 to t end, and let's do 50, I don't know. All right, cool. So we have our t-plot, and then we need to get our plot of concentration, so CA plot and temperature plot, that is equal to our res dot sol of our equation. Whoop, 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 whoop. Sorry, nope, just t-plot. Shift enter. Yes, yes, cool. All right, time to graph. All right, so we have our fig is equal to make underscore subplots. And then it's rows equal to 1, columns equal to 3. There's no shared anything, so it should just be that. What did I do before? Yeah, okay, cool. All right, enter. And then we go fig dot add underscore scatter. And we are going to do, oh, not equals, here. And we have x is equal to t-plot. Y is equal to, we have CA plot. And then we have row is equal to 1. Oh, wait, not 3, 2. We have 2. Column is equal to 1. And then we are going to leave it at that. Okay, cool. And then copy paste, change the variables. So instead of CA, it is capital T plot, and the column is column 2. Okay, we're going to switch it to be 500 iterations. See how that changes things. Wait a moment. Never mind, that's looking a little questionable. Wait. There we go. Okay. Okay. I don't know why I just looked at that graph and then was like, oh, that's right. No, okay, there we go. I forgot to take out the volume. So there we go. Okay. All right, that looks better. Cool. Glad I fixed that. I was looking back over my recording and I'm like, this does not look right. Why did I think this was right? But it's okay. I realized what I did wrong. So I just forgot to cancel out the volume whenever I put it into code. So here we are. This is part C with the graphs of our concentration and our temperature. Cool. All right. See you in the next one.